Hi, I'm Zach Langley, a PhD student at Rutgers University. In this talk, based on joint work with Sefer Asadi and Aaron Bernstein, I'll tell you about some new distributed algorithms for the load balancing problem. The talk is organized as follows. In the first section of the talk, I'll define and motivate the load balancing problem. I'll then tell you about our results and how they fit into the larger picture. In the last two sections of the talk, I'll describe our two main algorithmic results. In the load balancing problem, the input is a bipartite graph on clients and servers, where each client comes with a positive integral weight. The output is an assignment, a map taking each client to some adjacent server. The sum of the weights of the clients assigned to a single server is called the load of that server. There are several natural objective functions to consider here. The one we'll focus on in this talk is the min-max objective, in which we want to find an assignment minimizing the maximum server load. You can check that the assignment depicted on the right is optimal with respect to this objective. Although the min-max objective will be our focus, I want to briefly consider alternatives to point out an interesting property of the algorithms we'll develop. Another natural and well-studied objective is to minimize the sum of the squares of the server loads, which is equivalent to minimizing the L2 norm of the vector listing the server loads. The assignment on the right is no longer optimal with respect to this objective. The unique optimal assignment minimizing the sum of squares is the one being animated in now. Notice that this assignment is not optimal with respect to the min-max objective. This example shows that in general, these two objective functions are incomparable. However, somewhat surprisingly, for every input, there are assignments that are good approximations for both of these objectives simultaneously. In fact, there are assignments that are approximate for every LP norm simultaneously, including the L-infinity norm, which is the min-max objective we started with. The algorithms we develop in this work produce assignments with this same property. They are approximately optimal for all LP norms at the same time. To simplify the presentation, however, I'm going to focus solely on the min-max objective for the remainder of this talk. The load balancing problem has been studied in various applications. Let me highlight a couple listed here. Perhaps most notably, it's been studied under the name of scheduling jobs with restrictions. Here, one has some jobs and some machines, and the goal is to schedule the jobs on the machines so as to minimize the parallel completion time. In this application, jobs correspond to clients, their processing times the client waits, and the machines correspond to servers. Another interesting application, most related to our work here in the distributed setting, is the distributed backup placement problem. Here, clients on a network want to back up some resource on adjacent servers in order to minimize the total amount of backup data that any one server is responsible for. Before considering the load balancing problem in the distributed setting, let's quickly see what's known about the problem in the sequential world. When the clients are unweighted, it's well known that the problem can be solved exactly in polynomial time. However, when the clients come with weights, the problem is already NP-hard when there are just two servers, and moreover, it's NP-hard to obtain a better than 3/2 approximation. On the positive side, a 2 approximation is known, and we'll see the high-level approach of this 2 approximation later in the talk. We work in a standard distributed model called the local model. In this model, a network of processors collaborate to solve a graph problem on the network itself. Nodes initially only know their own neighbors. In each round, every node can perform some free local computation and then send and receive messages to and from its neighbors. Eventually, the algorithm halts and every node computes its local portion of the output. In our problem of distributed load balancing, at the end of the algorithm, each client will be responsible for assigning itself locally to some server. Finally, the performance measure in this model is the number of rounds of communication taken by the algorithm. We'll also consider the stricter CONGEST model. The only difference between CONGEST and local is that in the CONGEST model, the size of a message is capped at order log n bits. Let me conclude this introductory section by briefly contrasting the unweighted load balancing problem with the maximum cardinality matching problem. Notice that asking whether a graph has an assignment of load 1 is equivalent to asking whether its maximum cardinality matching matches all of the clients. I'll call such a matching client perfect. More generally, an unweighted graph has an assignment of load B if and only if this blown up graph, where I've duplicated each server b times, has a client perfect matching. In these distributed settings, it's known that computing exact maximum matchings cannot be done efficiently. One might hope then to use a 1 minus epsilon approximate maximum matching to bootstrap a good assignment. However, a 1 minus epsilon approximate maximum matching still leaves up to an epsilon fraction of the clients unmatched, and it's not clear how then to assign these unmatched clients. Although they form a small fraction of the total number of clients, they can still seriously mess up the maximum load once assigned. All of this is to say that the load balancing problem cannot be obviously solved just by using a 1 minus epsilon approximate matching algorithm. Let me now summarize prior work on this problem and our new results. There are two previously known algorithms for approximately solving the unweighted load balancing problem in the CONGEST model. The first, due to Shigrinov, Hanchkoviak, Szymanska, and Varziniak, obtains a 2 approximation in order delta to the 5th rounds, where delta is the maximum degree of the network. In terms of approximation factor, a 2 approximation is essentially the best we could hope for. But because the round complexity depends on the maximum degree, it leaves open the case of non-bounded degree networks. The next result, by Haldarson, Kuller, Pachemir, and Rawitz, obtains a log n over log n approximation factor in polylog n rounds. This is the type of dependence on n we would like in the round complexity for non-bounded degree networks. We obtain the best of both of these results for non-bounded degree graphs, a constant factor approximation in polylog n rounds. When clients are weighted, there's a simple reduction to the unweighted problem that results in a log n factor increase in the approximation ratio and runs in the same number of rounds as the unweighted algorithm. Via this reduction, all of the unweighted algorithms from the previous slide imply weighted algorithms with guarantees listed here. Interestingly, this is the state of the art. The simple reduction is basically our only tool for obtaining good CONGEST algorithms for weighted clients. Towards a better CONGEST algorithm, we also show a constant factor approximation in the less constrained local model for weighted clients. To describe our unweighted algorithm, let me start with a couple of definitions. The first definition is a slight generalization of a traditional matching, which we call a 1B matching. A 1B matching is a subset of edges that matches each client once and each server up to B times. On the right, a 1-2 matching is depicted in the solid edges. As before, we say that a 1B matching is client perfect if every client is matched by it. To motivate this definition, notice that a client perfect 1B matching is basically just an assignment of load at most B. Next, we define a vertex as saturated with respect to a 1B matching M if its degree in M is as large as possible. That is, a client is saturated if it has degree 1, and a server is saturated if it has degree B. On the right, all of the saturated nodes are highlighted in yellow. Notice that the top server here is matched but not saturated. Finally, we have the notion of an augmenting path with respect to these matchings. An augmenting path is a path that starts and ends at unsaturated vertices and alternates with respect to the matching. Now I want to state a key structural observation we make in this work, but before doing so, let me say something familiar. Suppose there exists a client-perfect 1B matching, and suppose that some 1B matching M is not client-perfect. We would then conclude that M is not maximum, and so there must exist an augmenting path. Our key structural lemma says that if we relax the assumption here so that the matching M has server capacity 2B, then not only does there exist an M-augmenting path, but there exists a short M-augmenting path, one of length order log n. In particular, the contrapositive states that if there exists a client-perfect 1B matching, then a 1-2B matching without an augmenting path of length order log n is necessarily client-perfect. I will basically show a complete proof of this lemma, but first I'll show you why it's useful. We need one other ingredient to apply this lemma in an algorithm. We need a way to compute a 1B matching without augmenting paths of length order log n. Fortunately for us, such an algorithm already exists. In precise terms, there's a CONGEST algorithm that computes a 1B matching without augmenting paths of length k or less in order k cubed log n rounds. This algorithm is an immediate consequence of two prior results. The first, due to Lotker, Petty, and Pachemir, gives an algorithm for the case of b equal to 1, that is, for traditional matchings. Later, Halderson, Kohler, Pachemir, and Roberts gave a reduction which, among other things, extends the algorithm of Lotka et al. To 1b matchings. We will just apply this algorithm as a black box. To develop an algorithm for unweighted load balancing, let's suppose we know b star, the maximum server load in the optimal assignment. Our algorithm would then be extremely simple. Just compute a 1-2b star matching M without augmenting paths of length order log n. By the key lemma, this algorithm produces a client-perfect 1-2b star matching, and thus if every client assigns itself according to this matching, the resulting assignment is load at most 2b star. By the no-short augmenting paths algorithm, this line can be implemented in polylog n rounds since we just apply it with k equal to order log n. Since we don't know the optimal value b star, we would like to guess and double. Here's a candidate algorithm. We try log n many values of b, namely every power of 2. For each such guess, we're going to compute a matching MB with no short augmenting paths. Notice that as soon as b is at least b star, MB will be client-perfect by the key lemma. Thus, if we just used the first client-perfect matching computed, we would obtain a good assignment. Unfortunately, this last line isn't implementable efficiently in the distributed setting. The condition here is too global. There is a simple fix. Rather than trying to coordinate on the first MB that matches all clients, we instead ask the client simply to locally assign themselves according to the first MB in which they are matched. This is the entire unweighted algorithm. Because all clients are assigned in the first iteration where b is at least b star, the load of any one server can just be written as a geometric sum up to 4b star, proving that the approximation ratio is a constant. To complete the proof of correctness, I owe you a proof of the key lemma. So again, here it is. To simplify the proof, let's just instantiate b to be 1, since the crux of the argument is already captured in this special case. So suppose there's a client-perfect 1-1 matching M star, and that some 1-2 matching M is not client-perfect. Since M is not client-perfect, there's some client C unmatched by M. We want to now find a short augmenting path from C. We really only have one move. Look at where M star matches C. If this server is not saturated by M, then we found an M augmenting path of length 1, and we're done. Otherwise, if the server is saturated by M, then M matches the server to 2 clients. Again, we look at where M star matches these 2 clients. If either of these 2 servers is unsaturated by M, say the top one, then we found an augmenting path of length 3. This is indeed an augmenting path since it starts and ends at unsaturated vertices by assumption, and because it alternates by construction. On the other hand, if both of these servers were saturated by M, then we can repeat this 2-step process of following M and then M star to obtain another set of servers, which are again candidates for ending augmenting paths from C. Notice that as long as we don't find unsaturated servers, the size of the sets of servers double in each iteration. Since the sets can't double in size more than log n times, we conclude that there must be an augmenting path of length order log n. That completes the proof for the case b equal to 1. How does the proof change for larger b? Well, the only difference is that when we follow M from right to left, the sets increase in size by a factor of 2b, and when we follow M star from left to right, the sets shrink back by a factor of b. The ratio between the sizes of consecutive sets of servers is still 2. Putting everything together, we have our first main result, a polylog n round constant approximate CONGEST algorithm for the unweighted load balancing problem. Finally, I want to tell you about our local algorithm. As a warm-up, let's start by looking at the 2 approximate sequential algorithm for weighted clients. The algorithm consists of 2 main parts. First, compute a fractional assignment, then round the fractional assignment into a proper one. Our local algorithm will follow the same high-level approach. However, the techniques for doing both steps will be entirely different. In the sequential algorithm, the fractional assignment is computed via a linear program, and the rounding step uses cycle canceling. Neither of these steps can be simulated efficiently in the local model. In addition to the high-level approach, our algorithm will also leverage the fact that the fractional assignments can be rounded into integral assignments without much loss. More precisely, The sequential algorithm gives the following promise. Any fractional assignment on unweighted clients can be rounded into an integral one where the load of each server increases by at most 1. I'm going to refer to this proposition as the rounding lemma. Let's now see how we can compute a fractional assignment in the local model before returning to rounding. Suppose we have as input the graph on the right. Notice that if we replace each client with a bunch of copies of itself, where the number of copies is given by the client's weight, then computing an unweighted assignment here gives a fractional assignment in the original graph. The only thing to check is that we can actually simulate the unweighted algorithm on this graph. Remember, these client copies are not actual nodes in the network. But still, any algorithm on this client duplicated graph is easy to simulate in local, since every message between real nodes in the network can just contain all the sub-messages with the relevant copy indices. I want to emphasize that this is the only step that does not run efficiently in the CONGEST model. To see this, just consider a client that has weight very large, like n. A server that wants to communicate with all n copies of this client in a single round can't do so in CONGEST because it only has one real link in the network to send messages over. So that's how we compute fractional assignments in the local model. Now I want to describe how to round them. Before we do that, we need a slightly more general notion of a 1B matching. Instead of 1B matchings, I'm now going to talk about 1 tau matchings. The difference is that tau is a function that specifies capacities on a server-by-server basis. For example, a 1 tau matching is depicted on the right, where server capacities given by tau are shown to the right of the servers. Saturated vertices with respect to a 1 tau matching are defined in exactly the way you'd expect. Servers and clients are saturated if their degree is as large as possible with respect to the 1 tau matching. The key lemma we saw in the previous section of the talk extends to 1 tau matchings too. If there exists a client-perfect 1 tau matching, then a matching which allows a factor of 2 slack in its server capacities is either client-perfect or contains a short augmenting path. The proof follows in exactly the same lines as before. So we've computed some fractional assignment f, and we'd like to round it into an integral one. I'm going to assume that every client's weight is a power of 2. Since we don't care about constant factors in the approximation ratio, this is without loss of generality. We'll round each weight class separately, so let's focus in on the first weight class. I want to consider the fractional loads induced by just this weight class by treating all clients as having weight 1. So these numbers f1 are just the fractional numbers of clients assigned to each server from this weight class. If we could compute an integral assignment with these server loads, and we could do so for every weight class, then we would be done. Because then after doing this for all weight classes, the combined server loads would just be equal to the fractional loads given by f. Of course, we can't hope to hit these numbers exactly. But the rounding lemma tells us that there's an assignment whose loads aren't far from these. In particular, there's an assignment that just increases the load of each server by at most 1. Now, we still don't know how to find an assignment with these loads in the distributed setting. But because the rounding lemma tells us that a client-perfect 1 tau matching exists, we can now invoke the key lemma, which says that every 1-2 tau matching is either client-perfect or has a short augmenting path. Thus, we can actually find an assignment with server loads 2 tau by computing a 1-2 tau matching without augmenting paths of length order log n. We do the same thing for every other weight class. Look at the fractional load contributed by just this weight class as an unweighted instance. Observe that, by the rounding lemma, there exists a client-perfect matching that increases each load by 1. And finally, leveraging the key lemma, compute an assignment with twice these capacities. Notice that this algorithm actually throws away the fractional assignment we start with. The only purpose of the fractional assignment is to set target loads for each server. Here's the entire weighted algorithm summarized on a slide. To see that this algorithm obtains a constant factor approximation, first notice that the fractional assignment f itself is within a constant factor of the optimum load. Then the load of any one server is basically doubled in this rounding procedure. The only thing to be careful of is this +1 term. Fixing a server, this +1 can only contribute one additional client of each weight, and so the geometric sum of potential new load is at most twice the maximum client weight. With that, we have sketched the constant approximate polylog n round local algorithm for the weighted load balancing problem. To wrap up, on the right are the main results of our work. In this talk, we covered the unweighted CONGEST algorithm and the weighted local algorithm. The key structural observation that we exploited in the design of our algorithms is the key lemma on the left. The natural next step left open by this work is to obtain a constant factor approximation in the CONGEST model when clients are weighted. Here, we're really only missing one building block, and I'm happy to talk more about this missing piece if anyone's interested. Thank you.